Hello, this is Jonathan Gardner, and in this video we're going to cover the first section of Chapter 2. Chapter 2 covers motion in one dimension. And when we're studying physics, the field of kinematics, so kinematics just means motion, the same as like cinema is the Greek word for motion or movies, right? And in this chapter we're going to look at only one dimension. We're going to be able to build off of this to all kinds of motion in three dimensions, rotational motion, and oscillations, right? And so in this book, they categorize motion into three types of motion. They say there's translational motion. That's motion like from side to side, up and down. There is rotational motion where something's spinning like this. And then we have vibrational motion where there's like recurring motion that just repeats back and forth, back and forth. And while we study translational motion, to keep things simple and to maintain our sanity, we're going to only deal with particles, right? And we're going to treat objects as particles. And what a particle is it has zero size, but it has in whatever mass it has. So particles have a definite position because they have no size, right? So they don't occupy space, for instance. And we talked earlier, I think in section 1.2, about models. In physics, we use models to greatly simplify the amount of thinking we have to do. You apply the right model at the right level, you can get good answers that are correct without being, entirely accurate. Like we would consider for motion in one dimension, we might consider a car to be a particle. Well, a car is definitely not a particle. It has, mass and volume and all these things. But we're going to treat it like a particle for particular kinds of motion. We're going to be able to deduce certain properties of motion by analyzing, real world objects as if they were particles. So when we're dealing with motion in one dimension, we're going to talk about one of the dimensions. We're going to call it the x dimension. And that could be left and right, or it can be up and down. It can be even in and out of the page, right? But x is just one of the dimensions. There's y and z as well. And so we use the variable x to represent the position of the particle. And so we're going to set some arbitrary point to be the 0 point. And then we're going to say everything to the right is positive, everything to the right is left is negative. So positive x goes this direction and negative x goes that direction. And then we're going to need some kind of scale. So we'll say like this is probably about 1 inch, so 1 inch from the origin there is, we're going to say x equals 1 inch, right? If the particle happens to be at that point. So he has in section 2.1, he has, I refer you to the textbook here. Remember, the textbook is free. It's available online. This is Surway and Jewett's Physics for Scientists and Engineers, 9th edition. So he has a drawing, kind of an animation, if you will, where it shows the car moving from position A at 30 meters, moves to the right to position B at around 50 meters, and then it starts moving backwards. It goes to position C, which is 38 meters, and then it goes to position D, which is 0, and it goes to position E, and then F, which is further and further to the left. And then he has a table that shows what time the car was at that position. So we're measuring the time. We're using the variable t for time, and in this case, they're measuring time in seconds. And so at t equals 0 seconds, the position was 30 meters. At t equals 10 seconds, that's position B. The x was 52 meters, and t equals 20 seconds, x was 38, and so on. So I refer to the textbook for that. And they have a nice little graph, and I'll kind of draw what the graph looks like here, help you understand what's going on here. So he has the graph, he has x on this axis, and he has t on this axis. So at t equals 0, this is position A. The x is up here somewhere, and then it goes up to position B, and then it goes down to position C, and then at position D it passes through the 0 line, because this is 0, and then it kind of goes down like this. E and F are down here. Okay, so I refer to the textbook for a more accurate drawing. I'm just kind of sketching things out here, right? And then he talks about the displacement, and he's going to use this symbol here. He says delta x. Delta is a Greek letter. It's the letter D, basically, duh. This is capital D. And delta x is going to be defined as the final position minus the initial position. So it's the difference between the initial and final position, right? So this is just x at the final position we're considering, that subscript, all that means is this x at that situation, and then this is x at the initial position. So if we're considering the displacement between, let's say we're considering the displacement between B and D, then we would take the final position, so where it ended up, that would be 0, and we'd subtract the initial position. And so the delta x, the change in x, the displacement, I'm going to write that word displacement, is just those two numbers subtracted from each other. Now, you will hear the word distance, and often you might think distance and displacement are the same thing, but they're not. Distance is the length of the path that the particle has traveled, right? So distance would basically be from here to here and here and here. It's going to increase as time goes on. It doesn't matter which direction you're traveling. Displacement tells you how far you've moved between two positions, whether it's positive or negative. Displacement could be 0. Like if you started, if you had a particle that started here, it went up, down, and ended up there, and you consider the displacement between those two positions, the displacement would be 0, but the distance would be, some large number. It's not 0. Displacement is an example of a vector quantity. So we're going to say a vector quantity. And it's a little bit premature to introduce vectors. I'm just going to talk a little bit about what they are. A vector quantity requires both a displacement, direction, and a magnitude, right? So in our case, since we're only operating on one dimension, the vector quantity, the sign of the number indicates whether it's towards the right or towards the left. And then the magnitude is just how big the number is. So plus 3 meters would be, 3 meters to the right. Minus 3 meters would be 3 meters to the left, right? And so a vector combines these two concepts into one. And by contrast, a scalar, and we do have scalar quantities like mass, scalar quantity only has a magnitude. It has no direction. Like mass doesn't matter which direction the object is facing. It's just part of what the particle is, and it doesn't matter where the particle is. The mass is the mass, right? So he explicitly calls out, he says, in our case, because we're using positive to the right, if delta x is greater than 0, then it's moving to the right. And if delta x is less than 0, then it's moving to the left, right? Now, one thing he wants to bring up, but if you're only looking at the table or the animation of the car, in example 2.1, it doesn't tell you what's happening in between those positions, right? We don't know, like in between position A and position B, the car could go all squiggly and end up at position B. We don't know what it actually does. We're assuming when we draw the graph that the object, the car follows, a continuous path that's smooth and has some other characteristics that we'll talk about later. It's like a realistic motion, if that makes any sense. Like objects tend not to disappear and reappear in different positions. They tend to move through all the points in between the two positions. The average velocity. So here's another concept. It's called the average velocity. And physics, just like medical science, you're going to memorize a lot of terms. Average velocity is going to be represented with the quantity v. It's a vector because the velocity could be pointing to the right or to the left. And when you learn about motion in 3 dimensions, it could be pointing any number of directions, right? So velocity in the x direction, we're going to put a comma. The average velocity, we're going to use the letters A, V, G to represent the average. This is defined to be the change in x over the change in t, the displacement in position over the displacement in time. That's the definition of the average velocity. This, when we're adding and subtracting 2 units of length, we end up with another unit of length. When we're adding and subtracting units of time, we end up with another unit of time. So this, what is it called? The dimensions of velocity is length over time, right? Okay, and that's a lot like, if you're familiar with speed, like speed is miles per hour. It's a unit of distance over a unit of time. Meters per second, kilometers per hour, whatever you want to use. the average velocity of a particle moving in one dimension can either be positive or negative or zero. Generally, we always consider the final position to occur later in time than the initial position. So this denominator is always greater than zero because time always marches forward, right? So D occurs later than B, C occurs later than B, and so on. So we generally only look forward in time. So the change in time is going to be positive. If the change in X is negative and the change in time is positive, then that means you're moving to the left. So the velocity is towards the left. But if the change in position is positive and the change in time is also positive, then we're moving towards the right. But you'll find that if you mess things up and you consider like B is the final and D is the initial, that just flips the signs around. You'll end up with a positive or negative. It won't change anything, right? Now, consider the concept of average speed, which is different. Average speed, we're going to say V average. That's defined to be the distance, total distance traveled divided by the amount of time it took to travel that distance, right? And that's not really a useful quantity that we consider very often in physics. This is the one that we really find useful. We use it for a lot of different things. Because of the way average velocity and average speed works, it doesn't tell you a lot about what's really going on with the particle. It doesn't tell you what's happening in between those two positions. It gives you a general picture, but it doesn't really give you a lot of details. He gives the example. It's a little bit complicated. So you're at an airport, right? And you're going to catch your flight, and it takes you 45 seconds to travel 100 meters down a long straight hallway towards your departure gate. At the 100-meter mark, you realize that you missed the restroom. You need to use the restroom. And so you go back 25 meters along the same hallway. You take 10 seconds to make the return trip. The average velocity of the travel that you took to get to the bathroom, well, you've only traveled 75 meters net, right? It took you 55 seconds, so it's about 1.36 meters per second. But the average speed is 125 meters divided by 55 seconds. So you get about 2.27 meters per second, right? So it doesn't really tell you like how fast you're walking. Maybe you were following somebody that was slow for a while, and then you passed him and you started walking really quickly. You know, maybe you stopped to check your flight schedule. Maybe you stopped to buy a snack. It doesn't really tell you that. It just tells you the average of the motion. Okay, quick quiz number 2.1. Under which of the following conditions is the magnitude of the average velocity of a particle moving in one dimension smaller than the average speed over some time interval? So we want to know which conditions give us the average velocity in one dimension is smaller than the average speed, right? So when is the average velocity smaller than the average speed? So it gives us case A. A particle moves in the plus x direction without reversing. Case B, a particle moves in the minus x direction without reversing. And in case C, a particle moves in the plus x direction and then reverses the direction of its motion. And then D, there are no conditions for which this is true, right? So when is the average velocity, remember the definition of velocity versus speed, when is the average velocity smaller than the average speed? Okay, so that's something to think about in those four. You'll have to consider these really carefully. You might want to draw it out on a piece of paper and think hard before answering these questions. This is something I want you guys to think about and solve on your own. And then we have example 2.1, calculating the average velocity and speed. I'm going to move it over here. I don't think this is going to take too much space. So we have find the displacement, the average velocity, average speed of the car in figure 2.1 between A and F. Okay, so the position at A is 30 meters, and the time at A is 0 seconds, and the position at F was negative 53 meters. I'm pulling this off of the table, and the time at F is 50 seconds. So pulling out a calculator, the average displacement, well, that's going to be the final position. So that's minus 53. Let's do this. Minus, sometimes it wants me to type something in for negative numbers. How do I use this calculator? Oh, there it is. Yes. Okay, I got to push that button. So it's minus 53 meters. And then the initial position was 30. So minus 53, minus 30. No, that's not correct. Minus 53. Let's try that again. 53 minus 30 equals minus 83. And then we're going to divide that by 50. Okay, so it's 1.66, but we're doing two significant, so it's 1.7 meters per second. Right. And then the average, they wanted the average, the displacement, displacement is just minus 83. Average velocity, average speed of the car. So we start at 30, we end up at 50. What is it? 22 meters from A to B, because this is 53. And then from 53 to negative, hold on a second here. So this, hold on. Let me go up to the chart here. Scroll up, scroll up, scroll up, scroll up. It's a lot of text. Okay, so this is, so it goes up to 52 meters here. And then down here at F, it ends up at minus 53 meters. And then over here, we're starting at 30 meters. So we go 22 meters up, and then from 52 to minus 53. So 52 minus 53, but 53 is negative. So 105 plus 22. So we did a total of 127 or 130 meters displacement or distance. And then we're going to divide that by the time, which is 50 seconds. So divide by 50, and we're going to do 2.5 speed average. This is the velocity average. And the final question that I think that was all the answers. Yes, that's all the answers they wanted. So the displacement was minus 83 meters displacement, 1.7 meters per second velocity, and 2.5 meters per second speed. Both of these were averages. And that's all there is to it. I wanted to talk really briefly about the homework problems. I encourage you guys to solve as many homework problems as you possibly can. Take those challenges on for yourself. I'm not going to cover them at all in these videos. If you have questions about them, you can ask me on my Discord channel. I'll put a link in the description. That's about all I had to say on that. You guys have a great day. Take care and bye-bye.